Okay, we're going to start talking about autoregressive models. Okay. Let's again assume that A sub t is a white noise process that has constant variance. Okay, AT has mean zero, constant variance, and autoregressive order process of order P is going to be written as that backshift equation 1 minus phi 1 b minus phi 2 b squared minus phi up to phi p b to the p. And again, that's for the all those operators apply to z of t, c sub t. So that's a polynomial, a backshift polynomial applied to z sub t. And the assumption in this model is that it is when we apply that to z sub t, we obtain a constant plus a sub t. Okay, the constant we can actually eliminate this constant subtracting it from zt, subtracting the mean from zt. Okay. Let me, before I go with the next equation. Let's see, I see there's something in the chat. Ricardo sent something in the chat for everybody. I don't know what that is. That's your WhatsApp chat, I guess. Well, if you look at this model, you'll see that essentially what we're saying is that we're taking zt minus phi 1, zt minus 1, minus up to phi p, ct minus p, equal to a constant, I'm going to call it here c, plus at, which is white noise. So in an essence, let's write this thing, we can write this thing as zt is equal to, I put everything on the other side, I say it's a constant, plus phi 1 ct minus 1, plus phi 2 ct minus 2, all the way up to phi p plus phi p zt minus p plus at. Okay, so if you look at this equation, this just looks like a regular regression equation, right? In multilinear regression, multiple regression, linear regression, we have a response which we express as beta no plus beta 1 x1 plus beta p xp plus epsilon. That's the regression model, right? This is the regression model. So that's why this model is called an autoregressive model, because we're essentially regressing z sub t onto itself. So we're taking expressing zt as a combination of the same variable, zt in the past, up to p periods back in the past, plus random noise. So it's essentially a regression model. That's why we call this thing an autoregressive model, because we're regressing the variable zt, which is observed time series, on itself in the past. Okay, so let's the constant here would be equal to 1 minus phi 1 minus phi 2 minus phi sub p applied to mu, multiplying mu, and in essence, what this means that the zt is assumed here to have a constant mean level. Okay, constant mean level would be expected value of ct is equal to mu. That's for every t. So we're saying that the mean of the process does not depend on t, right? So at least we have stationarity in the first order stationarity. And we can express this model to simplify notation. We'll use the backshift polynomial phi of b applied to zt with a tilde here. Okay, c tilde will be ZT minus mu. So we're subtracting mu to simplify that equation and assume that the mean will be 0. So if the expected value of ZT is mu, the expected value of ZT tilde will be 0, right? So we're centering the time series. Now, again, this is the expression for a backshift polynomial of order P. So this will be a model, an autoregressive model of order P. Of course, phi 1, phi 2, up to phi p are the model parameters, and those are the ones that we will be estimating. Okay. Now, this is I can write the model like this, which is what I just did. I write it as phi null plus phi 1 ZT minus 1. So instead of the constant, it's going to be phi null, phi 1 ZT minus 1 up to phi p ZT minus p plus AT, and that's why we call this an autoregressive model, because we are essentially writing a regression of the variable ZT in itself with the past values of ZT. Okay. Now, from this equation that we saw, in the one that I drew a little bit earlier, we only have a difference equation plus a random component. So that's what we have, a difference equation and a random component. Now, if you look at if you study a little bit of the difference equations, from the theory of difference equations, it is important to know if the difference equation reaches an equilibrium point or not. That's for deterministic difference equations. Okay, in deterministic difference equations, you need to make sure that the difference that difference equation reaches an equilibrium point. That would be the equivalent if we induce the random component, because we have this random component here. Now, if we induce the random component, then instead of talking about reaching an equilibrium point of the difference equation, we'll talk about stationarity. Okay, so dealing with the stochastic component, instead of referring to the equilibrium point, we'll refer to a stochastic equilibrium, which is a stationarity. Okay, so our difference equation has to satisfy certain conditions on the coefficients so that the model is stationary, or that we have stochastic equilibrium. Okay, which is the equivalent in the stochastic area of equilibrium point in the deterministic difference equation world. Okay, so the characteristic of whether an autoregressive process is stationary or not will depend on the roots of the characteristic equation phi of x equal to 0. Okay. If I equate phi of x to 0, the roots of that equation will determine whether I have stationarity or not, or non-stationarity. Okay. In the deterministic world, the difference equation phi of b, in the deterministic world, I'm ignoring here the random component, any difference equation phi of b, which is 1 minus g1b minus g2b squared and so on, can be expressed as 1 minus g1b minus times 1 minus g2b minus g1 minus g sub p b to the p. Now, g1, g2, and g sub p are the roots of this equation, right? If I equate this v of b, take b as a variable, like a variable x in a polynomial, then if I equate this phi of b equal to 0, then g1 up to gp are the roots of this equation. Okay, are the roots of that equation. Now, that's in the deterministic world. That's how you can express a difference equation. If we involve the random component, then instead of, and if this, if in the deterministic world, if a difference equation of this form is such that these roots of this characteristic polynomial, if the roots lie outside the unit circle or the unit sphere, it's a p-dimensional sphere. If the roots lie outside the p-dimensional sphere, we'll have equilibrium in the difference equation. Now, the equivalence in stochastic, when we inducing the stochastic component, is that the process will be stationary as long as the roots of this polynomial lie outside the unit sphere. Okay? Or I say it here outside the unit circle, but of course, if we are in p dimensions, it's really a p-dimensional sphere or hypersphere. Okay? But just to avoid complications in the language, we just say outside the unit circle. That is, g1 to the minus 1 will be greater than 1 in absolute value, and g2 to the minus 1 and so on. Okay, all the roots have to lie outside the unit circle. Now, and that's the condition for stationarity in a stochastic difference equation like the one we're dealing here in the autoregressive model. Now let's start studying a little bit the simplest model. It's an AR1 model, okay? That's the simplest autoregressive model. This model, ZT minus phi, but I only have one parameter here, right? Phi. I omit the phi1 because I only have one parameter. CT minus phi1 for times CT minus 1. I'll avoid saying ZT minus 1 tilde or whatever, right? We know that we'll be working with the center series, okay? That's why you have the tilde there. So what that model is, the AR1 model, is very simple. It says that the observation at time t can be expressed, this is the centered ZT, can be expressed as phi times the observation at time t minus 1 plus a random component plus white noise. Okay. This process in particular generates a time series known as a Markov series. Okay, the series that's generated by this model is a Markov series. Now, in this case, we only have one parameter. So the characteristic equation phi of, let's x equal to 0 has only one parameter, one phi there. And all we need for this is that the root of this polynomial lies outside the unit circle. In other words, phi needs to be less than 1 in absolute value. Okay, phi has to be less than 1 in absolute value. We only have one parameter here. So if in an AR1 model, the series is, or the model represents a series that's stationary if phi in absolute value is less than 1. That is, if the root of the polynomial lies outside the unit circle. Now, this series can also be represented in terms of a sequence of random errors. If you look at this case here, where I have ZT is actually 1 minus phi b inverse times AT, okay, applying that to AT. That is, if phi is less than 1 in absolute value, if phi is less than 1 in absolute value, then I can express this polynomial as 1 plus phi squared plus phi cubed and so on. Okay, so if phi is less than 1, then I can express the inverse of this polynomial as 1 plus phi 1 AT minus 1 plus phi squared AT minus 2 and so on. In other words, it's going to be 1 minus phi b inverse is going to be 1 plus phi b plus phi square b square. Remember, b is only an operator. It's not it's not playing the role of a variable here. Times at. Okay, when I multiply that by at, so I get at plus phi 1 at minus 1 plus phi square, and now I have b square. So it's at minus 2 and so on. Okay. Now, phi is less than 1, so that the expected value of zt, we know that is equal to 0. Okay. And gamma 0 is the variance of CT, but the variance of CT, if I use compute the variance of CT tilde here, it's remember the ATs are independent, and that's the only random component here in this equation. So that will be the variance of AT plus phi times the variance, phi squared times the variance of AT minus 1, plus phi to the fourth, the variance of AT minus 2, and so on. So that's going to be this expression here is sigma sub a squared, where sigma sub a squared is the variance of AT times 1 plus phi squared plus phi to the fourth plus and so on. Okay. And that is exactly the same as sigma squared divided by 1 minus phi squared. That is sigma squared sub a times 1 minus phi squared to the minus 1, right? Because if phi is less than 1 in absolute value, definitely phi squared is going to be less than 1. Okay, phi squared is going to be less than 1, so I can express this polynomial as 1 minus phi squared inverse, or to the minus 1. So that's the condition for stationarity, and this in the AR1 model, is that the root of the characteristic polynomial phi of b equals 0, that root is outside the unit circle, that is that phi, in this case only have one root, is less than 1 in absolute value. We're okay up to this point? Okay. Now let's compute the autocovariances. The autocovariances, since zt has mean 0, then the autocovariance between zt and ct plus k is going to be the expected value of zt times ct plus k, because we center the series and they have expected value of 0. So if I replace zt by its equation, which is at plus phi 1 and so on, and at plus k is at plus k plus phi 1, at plus k minus 1, and so on. And now I do the products, okay? When I do these products, when I multiply all these terms here by these terms in this second polynomial, when I do that multiplication, all the terms where the subindex for a is different, when I'm multiplying ai times, every time that I multiply ai times aj with I different from j, its expected value is going to be 0, right? That expected value is going to be 0. So all the cross product terms where the subindex of A is different, then will be 0. So if I eliminate all those terms, all I'm going to be left with is with the sum from I equals 1 to infinity of phi to the I times phi to the k plus I, plus phi k, right? Because when I multiply at times at plus k, when k is equal to 0, I have at squared, right? And here I would have at times at plus 0 minus 1, at minus 1. The expected value would be 0, and so on. Okay, and then I take the terms with phi at minus 1. When the only term that's going to be different from 0 is when the subindex here is equal to the subindex here, and that the expected value is going to be sigma squared sub a. Okay, is going to be the variance of a. So that's just the term when phi I is multiplied by phi k plus I. This I equals 1 through infinity. Okay, and this is the case where k is equal to 0, really, where I is equal to 0. Okay, if I is equal to 0, then I have phi to the k. Okay. Now that's so the covariance, the covariance between ZT and CT plus K is this thing here, which you can write as sigma squared times phi to the K times the sum of J equals 1 through infinity of phi to the 2I. Now, this will converge if phi is less than 1, right? And this thing will converge if phi is less than 1. Otherwise, it would diverge. That sum would diverge. But we're assuming here that phi is less than 1 in absolute value. Okay, so the variance doesn't depend on k. It's constant, and the variance all the covariances are constant and do not depend on t. They only depend on k, the separation between the separation in time. Okay, and that's what it says here. Since phi is less than 1, then I can write down gamma sub k as sigma squared phi to the k divided by 1 minus phi squared, because this term here, this sum, is 1 minus phi squared to the minus 1. Okay, because of the value, if phi is less than 1, phi squared is also less than 1. So this is going to be equal to phi times gamma k minus 1. So the autocovariance of at like k separation between two observations, two data points, the autocovariance is going to be phi, which is the coefficient, the parameter that determines this model, times the autocovariance of k minus 1 lags. Okay, so it depends on the autocovariance k minus 1 lags apart. Okay, now remember that the autocovariances are symmetric around 0. That is the autocovariance whether I move k periods ahead or k periods behind, the autocovariance is the same. Okay, the autocovariance is the same. So I can write down gamma sub k, the autocovariance of lag k, as sigma squared, which is the variance of the ATs, times phi to the k, divided by 1 minus phi squared. Okay, or you can write it as gamma sigma squared sub a times phi to the k, absolute value of k, times 1 minus phi squared to the minus 1. That'll be the covariance. Okay, and I can write this thing down like this as 1 minus phi squared to the minus 1 because phi is less than 1 in absolute value. So the autocorrelations, when we take the covariance and divide it by the variance, what we end up is with only phi to the k, right? If I have the covariance and divide it by the variance, I'm really dividing what? I'm taking the covariance of lag k, which is sigma squared sub a times phi to the k in absolute value. Okay, it's absolute value times 1 minus phi squared to the minus 1. And then I'm going to dividing that thing by gamma 0. And gamma 0 is when k is equal to 0, right? So that will be sigma squared sub a. Gamma 0, k is equal to 0, that will be phi. Okay. And that will be 1, sorry. It's phi to 1. That will be times 1 times 1 minus phi squared. That will be minus 1 to the minus 1. And that's just equal to phi to the absolute value of k. Okay, so the autocorrelations, if you see here, the autocorrelations at lag k, it's just going to be phi, the parameter for the AR1 model raised to the power absolute value of k. Since phi is less than 1, what's going to happen with these autocorrelations? They're going to be dying very fast, right? They should die very fast because phi is equal to because phi is less than 1. Okay. Now, this is an example of an AR1 process with phi equal to 0.8. Okay. First of all, the first autocorrelation, rho of 1, rho sub 1, that is the autocorrelation lag 1, is going to be equal to 0.8, right? Because it's phi to the absolute value of k. So that's the first autocorrelation, 0.8. You can see it here in this graph. This is the autocorrelation function. Then the second autocorrelation is going to be phi squared, 0.64, right? Because phi is 0.8, so it's going to be 0.64 and so on. So there's a fast, this autocorrelation function is decreasing exponentially to 0. Okay, that's an AR process with phi equals to 0.8. If we change the size of the sign of the coefficient, we use the same 0.8 for the AR process. All that's going to happen is that the autocorrelations are going to alter in sign. Okay, because when I raise, if phi is negative, then when I raise it to an even power, it'll be that'll be give us a positive autocorrelation, and if it's an odd power, it's going to be a negative autocorrelation. Okay, but as you can see, it's essentially the same thing. When k is equal to 1, I have minus 0.8, and then when k is equal to 2, I have 0.64, and so on. Okay, so it keeps alternating in sign. So the coefficient, the parameter phi, determines whether the model represents a stationary series, which in this case it does because its phi is less than 1. And the sign of phi determines how the autocorrelation function is going to behave. Now, this type of behavior is the one that we're going to be using to help us identify which type of model is an appropriate model for the time series that we'll be analyzing. We'll need other tools because we'll see later, it's very difficult to distinguish just based on the autocorrelation function. If I'm just based on the autocorrelation function, it's going to be very difficult to distinguish whether I have an AR1 process or an AR2 process. Okay, but we'll use another tool that's called the partial autocorrelation, which we'll study later. Okay, so far we're okay.
Yep.
Okay.
Yes.
Good. Now let's look at the AR2 model, and then we'll look at the generalization of ARP models. Okay. This is an AR2 model. So we have dependence on ZT minus 1 and ZT minus 2. Okay. That's a model. It's our polynomial. That's this is phi of B CT tilde is equal to this thing. So this is my polynomial now, phi of B equal to AT. Now, again, this is it's autoregressive order 2 because I can write this thing down as ZT tilde equals to AT, oops, sorry, equals to AT. No, I lost my pen. Phi 1 ZT tilde minus 1 plus phi 1 phi 2 ZT tilde minus 2 plus AT. Okay, so it's a regression with two variables predicting this response. Okay, where CT depends on the previous two observations. Now, for this process to be stationary, again, this follows from the theory of difference equations, okay? All this follows from theory of difference equations. For the process to be stationary, we must have that the determinant of one of the matrix that has -1 in the diagonal, then has phi2 of the diagonal, that determinant is greater than 0, and also the determinant of a matrix that has -1 of the diagonal, and then you have phi2, phi1, and then you have phi1, phi2, phi1, phi2, phi1. Notice the pattern. If you look at this right-hand column, you have -1, phi1, phi2, phi1. Okay, so you repeat phi1 here. It's the same pattern that you have here: -1, phi1, phi2, phi1. Okay, then for the second column you have zeros, and then you have phi2 and phi2 here. Okay, and then for the third column you have the phi2 here, and you have a 0 there and 0 there. That pattern will be the same pattern that we use for the generalization of an ARP model to determine whether the ARP model is stationary or not. Now, these conditions, the fact, if you compute the determinants here, you can show that the conditions that these two determinants be greater than 0 are equivalent to the conditions that phi2 is in absolute value less than 1. Phi2 plus phi1 is less than 1. Notice here that I don't have the absolute value. Okay. Here it's in absolute value, phi2 is less than 1. Phi2 plus phi1 is less than 1. And phi2 minus phi1 is also less than 1. Okay. So those three conditions are equivalent to these two determinants being greater than 0. So if for a model we have that these conditions hold, then the process that model represents is going to be a stationary process. Is it from my iPad? Okay. Now, since the mean of this AR2 process is 0, because we're subtracting, remember we're taking ZT tilde, which is ZT minus its mean. So the mean is going to be 0 of this AR2 process. All we need to completely characterize the autocovariance, the process. See, remember that we're going to be focusing on the first two moments. So we know the first moment is 0. So we need to determine or characterize this process is going to be the second moment, which is the variances and the covariances. So the covariance function, gamma sub k, in the particular case where k is equal to 0 is the variance, where the gamma sub k, which is the covariance between CT and CT plus k, is going to be phi1, expected value of CT plus k minus 1, plus phi2, expected value of CT plus times CT plus k minus 2, plus the expected value of CT times AT plus k. Okay. Now, this term here is simply when k is equal to 0, I have ZT and ZT minus 1. So that's the autocovariance of lag 1. Okay. So when k is equal to 0, I have ZT times ZT minus 2. So that's the autocovariance of lag 2. That's this gamma 2. And the last term is when the expected value of ZT tilde times AT plus k, it's going to be just the variance, right? When k is equal to 0, is ZT times AT. And the AT, we know that it's independent. CT depends on AT only. So it's expected value of AT plus k squared. Okay, because all the other terms will not be multiplying AT. So that would be sigma squared, because k is equal to 0. And if k is greater than 0, remember, it's this is symmetric around 0. So we don't have to, we normally compute only for k positive. Okay? And the charts that you see for the correlation, the autocorrelation functions, you will always see only one side from 0 on and not to the left of 0 because they're symmetric. So we have this is going to be for k greater than 0. That's going to be phi 1 gamma k minus 1, okay, plus phi 2 gamma k minus 2. And you get it from here. If k is equal to 1, you have CT, and CT plus 1 minus 1, CT minus 1 is gamma 1, gamma k minus 1. When k is equal to 1. When k is equal to 1, I have CT and CT plus 1 minus 2, which will be gamma sub k minus 2. Okay, that's the autocovariances, and those will be for k greater than 0. These autocovariances. Okay. Now, if gamma null, that is the variance. If the variance is finite, and it will be finite as long as the conditions on the determinants hold, we can divide the autocovariances by gamma null, right? If gamma null, which is the variance, is finite, we can divide the autocovariances by gamma null to obtain the autocorrelations. And that division, that ratio of the autocovariances by the gamma null yield what's called the Joule-Walker equations. The Joule-Walker equations are very important equations because they relate the values of the parameters phi 1 and phi 2 with the autocorrelations. So these are the Joule-Walker equations. It says that rho 1 is phi 1 plus phi 2 rho 1, and rho 2 is equal to phi 1 rho 1 plus phi 2. And in general, for k greater than or equal to 3, rho sub k is going to be phi 1 rho k minus 1 plus phi 2 rho k minus 2. Okay, so now notice this model here. Notice this model, and remember what that polynomial phi of b was. So if we write this thing like, if I write rho k, I'm going to put everything on this side. Phi 1 minus phi 1 rho k minus 1 minus phi 2 rho k minus 2. Okay, if I put it all on one side, that's exactly as the same thing as having the polynomial phi of b applied to rho sub k, where b is going to be operating on the subindex k. So the autocorrelations will behave according to the model that we're talking, according to the AR2 model. So the coefficients of this AR2 model will determine the behavior of the autocorrelations for lags k greater than or equal to 3. Okay. Now, the Joule-Walker equations are used not only to, of course, they relate the parameters with the autocorrelations, but we'll see when we estimate the model, we do not know what phi 1 and phi 2 are. Now, the algorithm to estimate the parameters is going to be based on maximum likelihood, and it's a nonlinear function that has to be optimized by numerical methods. So these equations are also used to determine initial values for phi 1 and phi 2. So when we estimate this thing, the algorithm uses these autocorrelations, sample autocorrelations, to get the initial values, okay, using the R1 and R2. The sample autocorrelations of orders 1 and 2 will be used by the algorithm to establish initial values, okay? And that's a model with two parameters, phi 1 and phi 2. Now, it can be shown that phi1 squared plus 4 phi2, see, if this happens, if phi1 squared plus 4 phi2 is greater than or equal to 0, then all autocorrelations will tend exponentially to 0. All of them will be positive if the first one is positive. So if the first autocorrelation is positive, then all of them are going to be positive. But if the first one is negative, they will alternate in sign, similar to what we saw in the AR1 process. Now, if this doesn't happen, if phi1 squared plus 4 phi2 is less than 0, then the autocorrelation function will show a sinusoidal type pattern converging to 0. Okay, so this, whether this is greater than 0 or greater than or equal to 0 or less than 0, will determine the type of pattern that we see in the autocorrelation function. Okay, so if this happens, we'll see sort of a sine wave type pattern converging to 0. Now, from the Joule-Walker equations, we can see, we can relate the parameters now to the autocorrelations. And again, when we have in an algorithm, when we're trying to estimate, what we're going to use maximum likelihood to estimate the parameters, then we'll phi1 hat initial, I'm going to put an I here for initial, is going to be R1 times 1 minus R2 divided by 1 minus R1 squared. Okay, and phi1 will be the same thing. So we can use these equations, the Joule-Walker equations, to get initial values for the parameters. Okay, so that the algorithm will converge faster if we have good initial values for those parameters. We don't have to worry about computation. In fact, yeah, that's for you to know that that's essentially what the algorithm does. But it's no concern for the time series we're dealing with in this class. Computation time is nothing. It's really nothing. Okay. Now, if the series is stationary, then we know the conditions on phi1 and phi2, because that's given by the Joule-Walker equations, and that determinant, the two determinants will be greater than 0. So if the series is stationary, then rho 1 is going to be less than 1, strictly less than 1. Rho 1 squared is going to be less than rho 2 plus 1 divided by 2. And rho 1 will always be between minus 1 and 1. That's not new. I mean, in fact, what it says is that rho 1 is also going to be strictly less than 1 in absolute value, right? So that condition holds when if the series is stationary, this is going to happen. Now let's consider three processes here. We'll consider this process that has 1 minus, here we know the parameters, right? We know phi1 and phi2. I'm generating the data. We'll look at the script and we'll generate this data. 1 minus 0.9. So in this case, phi1, so in this first case, is phi1 is equal to 0.9, and phi2 is equal to minus 0.2. Minus 0.2. Okay, in this case. In this second case, phi1 is equal to 0.8, and phi2 is equal to minus 0.6. And in this last case, phi1 is equal to minus 0.8, and phi2 is equal to minus 0.16. Okay, I intentionally did this thing here because remember the equation is 1 minus phi1 minus phi2. So when you see a plus here, that means that phi 2 is negative, right? So let's look at these three processes. Let's look at how their autocorrelation functions look like. The first two autocorrelations are given by these equations. These are the initial values, right? Because remember, for k equals 3 and on, the autocorrelations behave according to the model. Okay, so the first two are given by these equations, and then the row 3 behaves like row 3 is equal to phi 1 row 1 row 2 minus plus phi 2 row 3 row 1. Write it down. Remember that the model is 1 minus phi 1 b minus phi 2 b squared. So we know that for k greater than or equal to 3, we know that rho sub k is going to be equal to phi 1 rho k minus 1 plus phi 2 rho k minus 2. Okay, that's for k greater than or equal to 3. So once we have the first two, we know how to compute the rest of the autocorrelations. Okay. So for the first process, the first two autocorrelations are 0.75 and 0.475. And the ACF for the first process looks like this. This is the first process. That's it. The autocorrelation function looks like this. For the second process, it looks like this. Notice that there is a sine type wave behavior dying to 0. And the third one, we have an alternating sign in the autocorrelations. And you can check the conditions of that we saw earlier, of which if this, you can check if phi 1 squared plus 4 phi 2 greater than or equal to 0 or less than 0. And the second case that we saw, the sine cosine wave, we see that the second condition is the one that's holding, because we have this sine wave that's sort of dying out to 0. Okay. Now let's generalize this thing. Let's see how we're doing in time. Let's generalize this thing. Let me take a look very quickly at the scripts that I have in Brightspace. ST04. Let me take a look very quickly to this thing. ST04 scripts. I just wanted to make sure that you have that the same script here. This is script. I'm not going to go over this script now. You have it in Brightspace. All I'm doing here is I'm generating random the AR processes. Okay, I'm generating AR processes and just plotting their ACF, the series and the ACF. But we'll go into a different script next. When we look the moving average processes, we'll look at these. There's a script that you have in Brightspace. I don't have it here, but it's here in Brightspace. That's to simulate ARMA processes, autoregressive moving average processes. Well, that script will go into that script in detail, because that's going to be very useful for model identification. But we need to talk about the moving average processes first. So we'll finish AR processes today. and then hopefully we'll cover the MA processes next time. If we have time now, we'll go with one of these scripts. So let's look at the generalization to an ARP process. And the ARP process, it's just looks exactly like the same. That it's but we have dependence on ZT. ZT depends on ZT minus 1, ZT minus 2, up to ZT minus P. Where CT is, again, CT tilde is ZT minus mu. If the process to be stationary, then the roots of this characteristic equation must fall outside the unit P dimensional sphere. Okay, so the conditions are the same. The roots of the characteristic equation must lie outside the unit sphere. And this will happen if the P determinants that are equivalent to the ones we saw for P equal 2. So for P equal 2, we have two determinants, right? Are greater than 0, the first one, the second greater than 0. For an autoregressive process of order P, we'll have P determinants that have to satisfy the condition that the determinant is greater than 0. The patterns can be extended from the AR2 process. It doesn't make sense for us to go to the development of the pattern here, but these are the conditions that must be satisfied in order for the process to be stationary. Okay, and the Joule-Walker equations also extend to the to the ARP process. Now, in the AR2 process, we have two Joule-Walker equations. In the ARP process, we have P Joule-Walker equations that are derived from the determinants, the P determinants that have to be computed to determine if we have stationary process or not. But again, the important thing here is that it relates the autocorrelations with the parameters of the model. And just as in the case for k equal to 2, remember in the case of k equal to 2, we have the first two Joule-Walker equations to compute R1 and R2, row 1 and row 2. And then the third on, from the third autocorrelation, fourth, the fifth, and so on, we had the model, the AR model, determined the behavior of the autocorrelation function. The same thing happens here. For k greater than P, so for the first P autocorrelations, this is how you compute the autocorrelations. Okay, for the first P. Once for k greater than P, the autocorrelations are determined by the difference equation, by the polynomial, by the same backshift operator equation that determines the model. See, remember in this case the model was 1 minus phi 1 b minus phi 2 b squared minus phi p b to the p. That was the model, right? CT equal to AT. Well, this same model, for k greater than P, we have that row k, we have that 1 minus phi 1 b minus phi 2 b squared minus phi p b to the p applied to row k. This equation determines the behavior of the different autocorrelations. So it's the same thing that for the AR2, except that now k can be greater than 2. Okay. Now, of course, if k is very large, if p is very large, we'll look at alternative models because we don't want to estimate too many parameters. We need we'll be looking for parsimonious models. Okay. Have all of you heard the term parsimony or parsimonious models? Or has somebody not heard the term? before?
I don't really remember.
Okay. The term parsimony what that means is that we want to have models that are as simple as possible. So a model, if you have two models that are closely representing some process, and one has 3 parameters, the other one has 5, we will go with the one that has 3 parameters. So we want parsimonious models. Okay, so we will always be looking for parsimony in the models, when parsimonious models, that is models that are as simple as possible to reflect the reality. The models are always wrong. I don't know if you've heard that phrase. That's attributable to George Box. He said that all models are wrong, but some are useful. That's attributable to George Box, GEP Box. And that's true, because a model is just a representation of reality, but no model can reflect reality completely. So all of them are wrong because they are just representations of reality, but some of them are useful. And we're going to be focusing on models that are useful, and to be useful, they also need to have that characteristic of parsimony so that they are simple enough. Okay. So that's the term parsimony. Now, we saw earlier that if the process is stationary, then we can express it as a sequence, a linear combination of white noise in the time t minus 1, time t minus 2, and so on. We saw it with the AR1 process, right? Because we saw in the AR1 that if I have my process is 1 minus 5b ct equal at. I'm going to remove it. I'll leave the wiggle here. If phi is less than 1 in absolute value, that is, if the root of the polynomial lies outside the unit circle, then I can express this as zt can be expressed as 1 plus phi 1 b plus phi 1 b squared plus, and there's a sequence, an infinite sequence here applied to at. Okay, the same thing happens for an AR2 model. Once we have the roots of the equation, we can write we can put the polynomial on the other side of the equation, applying to at. So any stationary process can be represented as a linear combination of white noise, present and past. Okay, assuming that present is at and past at minus 1, at minus 2, at. This polynomial will represent this polynomial by psi, capital psi of b applied to at. Okay, so the polynomial psi of b will be minus 1 minus psi 1b minus psi 2b squared minus, and so on. Okay, so if you take this process, the AR1 process here, if you take this process, then in this process, what happens? Psi 1, psi 0, well, I'll start with psi 0 is equal to 1. Then psi 1 is equal to phi 1. Psi 2 is equal to, I'm sorry, I missed a square here, is equal to phi 1 squared, and so on. Okay, so any stationary process can be expressed in this form as a linear combination of white noise, present and past. And we'll be denoting by that representation, we'll be using the polynomial capital psi to denote that representation. Now, given stationarity, the ARP process can be expressed with either p parameters or an infinite number of parameters. Okay, the same process can be have both representations. If it's stationary, I can represent it with p parameters or with an infinite number of parameters, psi1, psi2, and so on. Because of parsimony, we will want the representation that has a smaller number of parameters. So we'll go with the with ARP representation. However, when P is very large, if we require a very large P, then there's an alternative, and that leads us to the phenomena that can be represented better by using a linear combination of random shocks, and that leads us to the moving average processes. Okay, so if P is very large, I may find another model with much less parameters than just a linear combination of white noise, of present and past white noise, and that gives rise to the moving average models. We'll call these types of models the moving average models. Okay, and those are the ones that we're going to study after these AR process, AR models. Okay, so let me erase this thing, and I'm going to go to the script. Since we have time, I'll go to the script. Okay. I'm going to generate that script. Let me see if it's the same that you have in Brightspace. Let me download this. I'll work with the one that you have in Brightspace. Okay, this is the one you have in Brightspace. Okay, focusing only on the AR process. Please download this script. And we'll focus now only on these AR processes. We don't have to download any file or anything because we're simulating data. We're just going to simulate AR processes. Okay. And these are the processes that we saw in the presentation, I believe. It's 0.8. This is an AR1. This is an AR1 process. AR1, AR2, AR3. Okay. Do you have the script already? I'm going to generate first I'm going to generate the white noise. Okay, I'm going to generate white noise first. So I'm going to set. If you're not ready, let me know so that I stop here. Hold on a second. This is a very, very quick script. See, I have the, I'm setting end, oh, Z not found. I haven't generated C. Paste. I'm going to generate 200 data points. Okay, I'm going to have from a normal distribution. It's a standard normal distribution. So I'm going to make generate in Z, which I should call A because that's going to be my white noise. I'm going to generate 200 random numbers from a normal distribution with mean 0 and the standard deviation 1. You can see the histogram of this thing of Z. And it looks symmetric and all that. Okay, but it's supposedly generation from 200 numbers from a normal distribution. Okay, now I'm going to generate. I'm going to go here, and I'm going to generate AR AR1 process, AR2, I'm going to generate 3 AR1 processes. Okay, I'm going to take n is length of z. Then I'm going to set initialize vectors with 0. Okay, so I initialize the vectors with 0 of the size 200, right? Because I'm going to generate 200. I have 200 random numbers there. So, and now I'm going to do. If you look at this thing, I sort of shorthanded this thing. I am assigning z of 1, the first random number, to AR1, the first model that I'm going to generate, the first observation, the second model, the first observation, the third model. So X, AR1, AR11, AR12, and AR13 have the same initial observation. And now I'm going to generate different models. I'm going to generate a model with phi is equal to minus 0.8, another model with phi equals to 0.8. So let me put a comment here. Here I'm saying that this is an AR1 model and phi is equal to 0.8, right? In this one is, I'm doing phi is equal to minus 0.8. And here I'm doing phi is equal to 0.3. And I'm going to generate, if you look at the equation, this is telling me the second observation for this first process is going to be 0.8, the prior observation, the first, for example, when I is equal to 2, I'm taking the first observation times 0.8 plus white noise, because Z only has white noise. So I generate this thing, and I'm going to generate the plots. I'm going to plot the 3 series and their ACFs. Okay. Now these are numbers that are generated randomly from an AR1 process. So all of the 3 are AR1 processes. These bands here represent the confidence bands, assuming that the autocorrelation is equal to 0. Now, if you look at the series, identifying a model based on the plot of the series is not easy. Okay, there's no way to know that this is an AR1 and this is also an AR1 and so on. But we know that looking at the ACF and the partial autocorrelation function. Now, you can see that in all cases, the ACF, the autocorrelation function, decays quickly. In this case, it's alternating sign because phi 1 in this case was negative, right? The first coefficient was negative. That's in the first case. Let me put this thing aside. Remember, the second case is minus 0.8. So that's why it alternates. And these are roughly minus 0.8. Remember, 0, you ignore the 0, okay? You ignore the 0 here. And we'll use a different function to generate the ACFs that will omit this 0. So from now on, here, ignore the 0. Ignore that. So you can see here that the exponential decay in these AR1 processes. Okay. Now, this one decays faster. Why? Because remember, phi in this case it's very small. It's 0.3, right? In this case, it's 0.3, so that's why we have faster decay in that series. In this one here. Now let's look at AR2 process.